Okay, so just to review exponential functions, the basic form y equals a to the x. A is going to be some constant. It's going to be some base. It has to be positive, right? You'll never see these with negative bases. I haven't in all my years, right? That's not a thing that we worry about. But so a will be some positive number, x besides 1, right? If it's 1, you don't really get much of an exponential graph at all. And then we're going to graph this, but it just helps if we know some things, like just to kind of review like just what's going on with things. And what you might think about here is, for example, just say you have something really straightforward like y equals 2 to the x power, right? We know it's an exponential function because it has an exponent or a variable in its exponent. That's what makes it exponential, right? So if you see a variable in the exponent, you're dealing with an exponential function or something related to an exponential function. Right? Something's going on there. But the thing we want to realize here is we look at this function y equals 2 to the x power, which is the first one on our table here, right? We're looking at there. If you're going to graph most things, if you don't remember anything about them, you can just make a table of values, right? You can plug numbers in, and you can do things that way. So what we can do here is we could say, well, let's put in generally a good starter set of x values is to go from -2 up to +2. Right? It doesn't graph everything always, and some things it does a really terrible job graphing, but in general, we tend to catch a lot of the points that we need. So for the first one, when you put -2 in, we're going to get 2 to the -2 power, which we should know how to do, but just to review that, if you have 2 to the -2, remember a negative exponent means you're going to take the reciprocal of the base, correct? So that would be the same as 1/2 squared, right? The reciprocal of 2 is 1/2. You square the top, you square the bottom, and we get 1/4, right? So we have this point, -2, 1/4, bless you. And then we can do the same thing with -1. So 2 to the -1 power is 1/2 to the first, which is just 1/2. What do you think 2 to the 0 is? What's anything to the 0? Yeah, it's actually 1. It's strange. It is, but it is. And then 2 to the first, hopefully we're good there, and 2 to the second. So what I want to point out here is if you look at all the y values, these are all positive numbers, aren't they? Like if I kept getting more, like obviously if I put 3 and 4 and 5, it's going to get more and more positive, bigger numbers, correct? But if you did -2 and -3 and -4 as your exponent, would it still be a positive output? Sure, because the operation is right, we flip it and then you square it, but if anytime you take any power of a positive, you always get a positive. So what that tells us is, and one of the most important things we want to figure out when we're dealing with an exponential function is where's this, there's going to be a horizontal asymptote there. Because if we kept going, we're going to get closer and closer to 0. Right? As x's get more and more negative, that fraction is going to get smaller and smaller. So it's going to approach some horizontal asymptote. So in this case, we have a horizontal asymptote at y equals 0. Okay, so that tells me that in order to graph this, just like we did with rational functions, if we're going to draw, when we draw our x-axis, let's go ahead and extend it on each end with some dashed lines to remind ourselves, hey, that's a horizontal asymptote, which is also an end behavior asymptote, just like we saw in our last unit. So here, 1, 2, 3, 4. Oh, I said I wanted to dash those, didn't I? Right, so that would be dashed to show us there is an end behavior asymptote. We plot our points, -2, 1/4, -1, 1/2. So we get these points. Now, in terms of our end behavior here, if we graph these, we know it looks like this, correct? It's really, my exponentials are really flat on one side and really steep on the other. So kind of a different here than we saw with rational functions is that the end behavior asymptote is this horizontal asymptote when we're going to the left. But when we're going to the right, there's no end behavior asymptote. So the graph will look something like that. Okay, and again, we have a horizontal asymptote. If you were asked about the end behavior, you would say the limit, I guess it was y, as x approaches positive infinity. So as we go to the right, it doesn't approach anything fixed, does it? It goes up forever. So this would be infinity. And then the limit of y as x approaches negative infinity, which asks us what happens as we go to the left forever. Right, that would be 0. It would just approach that line 0. So over here we have a horizontal asymptote. The end behavior is the output approaches 0, and then up here it goes to infinity. So that's good on that first graph, right? Now if they were all 2 to the x, we'd be done. We'd be like, oh, next logarithms. But unfortunately, we move them around a little bit. So let's see how we do that. It has this next one, and here there's a couple things that we can do. I personally don't use a lot of translations, but it is something that we've studied where and really the ones we're going to translate are pretty straightforward here. But if you remember, if we compare these two functions, that we have f of x equals 2 to the x, and then f of x, g of x equals 2 to the x minus 2 plus 3. This is what we call the parent function, and that's what we just graphed right here. Yeah. This is a shifted function. So just a quick review on shifting and how that works. Here we see that x was replaced with x minus 2. Does anybody remember what that would do in terms of the graph, how that would move it? 2 units, but which way? Now be careful, with the x's it's the opposite of what you think it would be. So this case, so since x was replaced by x minus 2, that means we shift right 2 units. What I always remember is whenever you're dealing with the x, things look the opposite. If you think back to factors and zeros and how you get an x minus 4 as a factor and then you get 4 as your 0, x is just sort of, and the reason that is if we know that when we did 2 to the 0 power, we got 1, correct? Over here on our original function. Well, if you wanted to do 2 to the 0 power again, you'd actually have to put in a positive 2 up here, is why that does that. So it shifts it over. Now the whole function had a 3 added to it. What transformation will that give us? It's going to be up 3, right? So since 3 was added to the entire function, that means we're going to go up 3 units. Now what that means is since we already know the graph or the table for this parent function, we can just go to that parent function on these pretty straightforward ones, and then we can just plug in, or we can just shift each of the points. So each of those x values, right, instead of having these x values, we're going to take all the x's and we're going to shift everything right 2 units. So negative 2 plus 2 becomes 0, right? And then negative 1 plus 2 becomes 1, and then 2, and then 3, and then 4. And then we're going to add 3 to the y values, right? The up, y is the up values. So the y values will become 3 1/4, 3 1/2, 4, 5, and 7. Okay, so again, if you know that parent function, you could pretty easily shift it to get the resulting function. Now, what else do you think moved up 3 units besides these points? Anybody? Well, we had a horizontal asymptote, correct? Think it moved up 3? It did too. Now, do you think it moved side to side 2 units or whatever? I mean, I guess. It's an infinite line that's horizontal. Like, you can move it side to side as much as you want. It doesn't do anything. But you did move it up. So in this case, our horizontal asymptote would now be at y equals 3. Right? And then let's go ahead and sketch our graph here. So, and you have a grid there on your paper. So here I'm going to put, again, a dashed line for our horizontal or our end behavior asymptote. And then from here, go ahead and plot these points: 0, 3 1/4, 1, 3 1/2, 2, 4, 3, 5, 4, 7. That looks like the same shape, doesn't it? Now we have it. We have different end behavior. So there we go with that one. So again, we just took this original graph, the original table. I guess I put it up. Right, here was the original. This was y equals 2 to the x. Right, you notice, if we look, a lot of times you can look at that y-intercept point and kind of judge it, the translation based on that. This was at 0, 1, and we said we moved it over 2 and up 3. So it's good that it's now at 2, 4. Right? That's where it would have moved to. So everything is just shifting there. Yeah, so let's go ahead and take a crack at some of these on this worksheet. On the front here, you have y 1/2 to the x power. Again, if you're we're going to graph them today, and what I want you to practice here is try making your table of your parent function, right? And when you're making that one, you can always go from -2 to +2 on your x values, and you'll get a nice graph. Then take that table, shift it, up, down, left, right, whatever the function tells you. That's going to produce a new function for you, or new points, and then you can go ahead and graph those. Okay, so with your table mates, let's go ahead and do that, give that a shot, and I'll be around to see if you have any questions.